This lesson is a general introduction to the flight deck to include primary and standby flight instruments and navigation displays. Let's begin our look around the flight deck with the clocks. The top window displays Greenwich Mean Time in a 24-hour format. The lower window displays elapsed time or chronograph time. Later lessons will explain how to set the clock. Use the elapsed time and the chronograph features. The Radio Distance Magnetic Indicator, RDMI, provides distance and bearing to the selected station. The RDMI has left and right DME indicators, a compass card with pointers, and left and right ADF VOR selectors. Heading reference indicates the current compass orientation, as determined by the heading reference switch. The heading reference switch is located on the center instrument panel. The switch is in its normal pre-flight position. In normal, switching between magnetic and true heading occurs automatically above 73 degrees north or 60 degrees south latitude. When approach is selected on the HSI panel, L for localizer is displayed on the DME. This indicates the distance to the localizer DME. The right side display works the same with the right HSI panel. The left and right ADF VOR selectors determine the reference for the pointers. The narrow pointer indicates left VOR ADF bearing. The wide pointer provides right bearing. This flag indicates a failure of the left radio or its signal. Similarly, this flag indicates a failure of the right radio or its signal. A heading flag indicates invalid heading information. From this RDMI, determine the mode selected on the HSI. Now let's discuss the primary air data instruments, beginning with the Mach airspeed indicator. The Mach airspeed indicator requires electrical power. And air data computer information. Mach is shown in the upper window. Below 0.4 Mach, the window blanks. Airspeed is shown by this pointer and displayed in the lower window. The minimum airspeed displayed is 30 knots. This pointer indicates maximum operating airspeed. Movable white reference bugs are also provided. This is the command airspeed bug. When the IAS Mach window is blank, the FMC sets the command airspeed bug automatically. If the IAS Mach window is open, rotating the mode control panel IAS Mach selector sets the command bug. Now let's look at non-normal displays on the airspeed indicator. Flags are displayed to indicate non-normal conditions. Touch any flag to hear a description of its meaning. This flag indicates the Mach display is unreliable. This flag indicates the VMO pointer is unreliable. This flag indicates the command bug is inoperative. This flag indicates the air data system is inoperative. Now let's look at the altimeters. The primary altimeters are electrical and receive signals from the air data computers. As you approach the altitude selected on the MCP, the altitude light illuminates within 900 feet of the selected altitude and extinguishes within 300 feet of the selected altitude. Turning the reference altitude control positions the reference altitude marker. Position the reference altitude marker to 540 feet. An off flag indicates the altimeter is inoperative. The vertical speed indicators are electrical. And receive signals from the Air Data Computer, ADC, and the Inertial Reference System, IRS. An off flag appears when the VSI is inoperative. Engine indications are displayed on the two CRTs on the center panel. The primary engine indications display on the upper CRT. The secondary engine indications display on the lower CRT. The engine display switch is on the forward electronic panel. This switch controls the display of the secondary engine indications. This knob controls the engine panel brightness. The outer knob adjusts the lower display, and the inner adjusts the upper display. More information on engine displays will be presented in Engine Indication and Crew Alerting System, EICAS lesson. The instrument source select switches are used to select alternative sources of flight information. These switches are covered in detail in another lesson. The IRS and air data switches affect flight instruments discussed in this lesson. The right ADC normally supplies information to the first officer's air data instruments. The left ADC normally supplies information to the captain's air data instruments. These flags appear when the air data computer fails. Select the alternate ADC. The right ADC now supplies the signals and the failure flags disappear. The left IRS normally supplies information to the captain's vertical speed indicator and the first officer's RDMI heading. The right IRS normally supplies information to the first officer's vertical speed indicator and the captain's RDMI heading. If a failure occurs, select the center IRS as the data source. The center IRS now supplies the information and the flags disappear. The Attitude Director Indicator, ADI, along with the various displays, and air speed tape are the subjects of forthcoming lessons and will be discussed in detail then. The decision height panels, which are used to enter the radio altitude decision height, are also used to control the ADI display brightness. Increase brightness on the ADI display. There are two CDUs located on the flight deck aisle stand. They are connected to the two FMCs installed in the airplane. The CDU is used by the flight crew to interpret communication with the FMC. Its use will be discussed in the FMC lessons. The HSI display panels are also the subject of forthcoming lessons. The various controls associated with the HSI include the HSI control panel, the MCP heading selector, and the FMC nav selectors will be covered in detail in later lessons. There are two HSI display panel brightness controls on the HSI control panel. The outer control adjusts brightness for the HSI display, and the inner control adjusts the brightness for the weather radar display. First, touch the outer control to adjust the HSI brightness. Now touch the inner control to adjust the weather radar display brightness. The VOR DME control panels are located here on the glare shield. Normally, VOR and DMEs are automatically tuned by the FMC. The VOR and DME can be manually tuned by selecting Manual on the VOR DME panel. Standby flight instruments serve as backups if the primary instruments fail. The standby attitude indicator is powered by the standby electrical system. This instrument has an ILS and back course selector and a caging control. Pulling the caging control aligns the horizon line with the airplane symbol. The ILS selector allows the display of localizer and glide slope information. Select ILS mode. Localizer and glide slope information are displayed. The back course mode reverses sensing for the localizer deviation pointer. It functions like the back course mode on other standby attitude indicators. A gyro flag means the attitude information is unreliable. Localizer or glide slope flags indicate the respective center receiver has failed. The standby airspeed and altimeter indicator inputs are pneumatic. Their static pressure source is the alternate static system. These instruments require no electrical power. The Electronic Flight Instrument System, or EFIS, combines the information displayed on all these conventional instruments and tuning panels. Into two rectangular display units, the Attitude Director Indicator, ADI, and the Horizontal Situation Indicator, HSI. Let's look at how the Attitude Director Indicator and Horizontal Situation Indicator show all this information. Each display combines the indications of several older style instruments into a smaller, easier-to-view area. Contrasting colors are used to make bugs and other indications easier to find on the black background. Before we look at the ADI, it's important to remember that this is only an overview of the EFIS. All indications are discussed in detail in other lessons. On older airplanes, you had separate airspeed indicators and attitude indicators. Separate panels and indicator lights showing auto-flight status and operating modes are combined into the ADI and shown here. The ADI combines all of this data into one display. Let's look closer at each of these indications. In addition to the conventional round dial airspeed indicator, the ADI has a moving tape display. Higher speeds are shown at the top of the tape. Current airspeed is shown here. An airspeed trend vector reacts to changes in airspeed. Various speed bugs to indicate takeoff speeds and assist in flap retraction are controlled through the CDUs. They augment the adjustable bugs found on the bezel of most airspeed indicators. The maximum airspeed pointer is replaced by a red and black band. In addition, minimum maneuvering and stick shaker speeds are also displayed. Selected speed indications are controlled through the Mode Control Panel, or MCP. The MCP is located here on the glare shield. These are the airspeed controls. Individual controls on this panel are discussed in other lessons. The attitude indication should look familiar. The ball-type slip skid indicator is now positioned just below the ADI display. Radio altitude is shown here instead of on a separate indicator. The rising runway symbol is displayed during ILS approaches. It is discussed in a later lesson.
Wind shear.
A pitch limit indicator, or PLI, has been added to aid in stall and wind shear recoveries.
Climb, climb.
TCAS guidance can also be shown. TCAS is discussed in a separate lesson. The localizer pointer and deviation scale are displayed when ILS frequency is selected on the ILS panel. Similarly, the glide slope deviation scale is displayed. The glide slope pointer is displayed when airplane track and the front course set on the ILS panel is within 90 degrees. Conventional navigation instruments usually included a horizontal situation indicator, or HSI, a secondary compass card with additional bearing pointers, and separate control panels for mode selection and navigation radio tuning. The HSI display combines all this information and much more into one area on one compass. The HSI mode shown here is called Centered Approach Mode and may look familiar. In this case, ILS approach information is displayed. Selected ILS mode and radio frequency information are also shown. Both VOR and approach have a centered mode, which displays a full compass rose, and an expanded mode with a partial compass rose. The expanded display is easier to read and allows room to display weather radar returns, as well as TCAS information. The EFIS control panel is used to select the desired HSI mode, change the displayed range, and to display ADF bearing pointers. A third mode is MAP. This is the recommended mode for flight and the one you'll use the most. It also has expanded and center modes. MAP displays navigation information from the FMCs. As the airplane moves, so does the map. Descent path guidance is also provided in MAP. Weather radar returns and TCAS information can be displayed in both map modes. MAP is a track-up mode. This is an important difference between approach or VOR, which are heading-up modes. A track-up display lets you always see the course you want at the top of the display, instead of off to the side as with high crosswinds. Take a moment to note the differences in the two displays. Ever wished you had an easier way to see your entire route right in front of you? That is what Plan mode is used for. Plan displays static map information. One important difference about Plan is that it is always oriented with true north up. The legs page shows the waypoint at the center of the display. By pushing the step line select key, you can move through the route segment by segment. Push the step key until RAFS is at the center of the display. Continue. Increasing the display range lets you see up to 320 miles of the route at once. Here the range is set for 40 miles. Now set the range for 20 miles. Decreasing the range and moving the display center allows you to look over an approach procedure hours away. Using Plan mode during normal route entry is covered in a later FMC lesson. Even though these two displays seem rather crowded and confusing, you'll soon see how informative and easy to use they are. The Engine Indication and Crew Alerting System, or EICAS, consolidates engine and subsystem indications. With the Crew Alerting System, this lesson discusses only the crew alerting portion of EICAS. The Crew Alerting System includes a Traffic Alert Collision Avoidance System, or TCAS, a Ground Proximity Warning System, or GPWS, and Airplane System Alerts. TCAS and GPWS are covered in other lessons. The Crew Alerting System includes 2 master warning and caution lights. Messages along with annunciator lights and gauge indications inform the crew of airplane status. Messages are displayed to the crew on the upper and lower CRT displays. Oral annunciations are broadcast over 2 flight deck loudspeakers located overhead. EICAS receives inputs from over 400 sensors on the airplane. These sensors continuously monitor the airplane systems, including engine parameters. 2 independent EICAS computers process the sensor information. EICAS then displays engine indications and alert messages on 2 cathode ray tubes, or CRTs. Alert messages are normally displayed on the upper CRT. These CRTs are on the center panel. Engine indications are displayed on both the upper and lower CRTs. These indications are described in the power plant lessons. EICAS messages alert you to non-normal situations. These messages display next to the primary engine indications. Because EICAS provides automatic monitoring, you do not need to constantly monitor the indicator lights in the flight deck for non-normal indications. The flight deck scan is simplified because the alert messages are centrally located. Crew alerting messages are divided into 3 categories: warnings, cautions, and advisories. Warning alerts are red and indicate the most critical problems. Caution alerts and advisories are amber and indicate less urgent alerts. Warnings require immediate crew awareness and prompt corrective action. Cautions require immediate crew awareness and require timely corrective action. Advisories are the least urgent and can be addressed when time is available. Master warning caution lights are on the glare shield. Both lights illuminate when a warning or caution message is displayed on EICAS. Also, a 2-tone oral warning sounds for warning and beeper sounds for a caution alert. The master warning caution light is a reset switch. When the switch is pushed, the oral is silenced. In addition to the EICAS message and the master warning or caution light and oral, all warning or caution alerts have associated discrete lights. These lights are located on the overhead panel, the forward instrument panel, and the aisle stand. Selected EICAS advisory messages also have associated discrete lights. Advisories do not have an oral alert. Let's look at a warning alert. When the alert occurs, select the master reset switch to silence the oral. Pressing the master warning reset switch has silenced the warning auric and extinguished the master warning light. This also resets the system for another alert. Notice that the EICAS message and discrete warning light remain in view and will remain displayed until the condition no longer exists. Now let's look at a caution level alert. When a caution level alert occurs, the caution beeper sounds, then automatically silences. You do not need to silence the beeper. An EICAS message is displayed, the master caution light illuminates, and the associated discrete light illuminates. Pressing the master caution light extinguishes the light and resets the system for another alert. Extinguish the master caution. The EICAS message and associated discrete light remain until the problem is corrected. Now let's see how advisories are displayed. Advisories are indicated by a message on EICAS. There are no oral alerts associated with an advisory. Advisory messages, like caution messages, are amber. They are indented one space on the message list to distinguish them from caution alerts. Notice from the previous EICAS alerts, the crew alerting messages are displayed according to how critical they are. The red warning messages appear at the top. The amber caution messages appear below the warning messages. Advisory messages appear indented on the list. Crew alerting messages are also arranged by their order of occurrence. The top message in each group indicates the newest alert in the category level. Alert messages are managed by the cancel and recall switches. You use these switches to control the alert message list. Selecting the cancel switch removes the caution and advisory messages from the display. Select Cancel. Notice that the warning messages remain displayed. They cannot be canceled. The recall switch can be used to redisplay the caution and advisory messages. Select Recall. The caution and advisory messages are replaced if the associated fault still exists. Whenever the recall switch is selected, a recall annunciation is shown momentarily. The alert area of EICAS has enough room to display 11 messages. If there are more messages than can be displayed on one page, the list is carried over onto an additional page. Selecting Cancel displays the next page. Display the next page. This page lists the oldest advisory messages. Notice that any previous warning messages are carried over from the previous page. Warning messages are not canceled. They are removed only when corrected. Let's look at how a new fault condition is displayed. A new alert message is placed at the top of its level on the current page. When the last page is displayed, the next push of the cancel switch cancels the caution and advisory messages. Cancel the caution and advisory messages. The recall switch is used to recall any previously canceled caution or advisory messages. Display the caution and advisory messages. Recall displays the first page of EICAS messages. Notice that the newest fault appears on page 1 at the top of its message group. Next subject is the EICAS control panel on the forward aisle stand. This panel is used to control the display presentation. Record unusual EICAS events. Select an EICAS computer. Adjust the brightness of the display. Manually display the reference thrust. and erase the displayed exceedance value. This lesson will discuss selection of EICAS computers, the brightness control, and the event record feature. Other features of the EICAS control panel are discussed in other lessons. The EICAS system includes two computers to monitor system sensors. Both simultaneously analyze system inputs. However, one of the computers is in control of EICAS displays. The left computer normally controls EICAS. The computer selection on the EICAS control panel is normally in auto position. In auto, if the left computer fails, control is automatically switched to the right computer. If the automatic feature fails to switch to the functional computer, manual switching is available. Select the right EICAS computer. Now only the right EICAS computer will display information on the EICAS displays. The brightness control allows you to control the brightness level of each display. The top selector controls the brightness of the upper display. Increase the brightness on the upper display. The bottom selector controls the brightness of the lower display. To adjust the brightness of a single CRT, turn one selector and hold the other selector stationary. To adjust the brightness of both CRTs, turn either selector. Both selectors move together. Increase brightness on both CRTs. Touch either selector to increase the EICAS brightness. To prevent distractions during takeoff, there are two EICAS alert inhibits. A caution inhibit that begins at 80 knots, and a warning inhibit that begins at rotation. The 80 knots caution message inhibit delays the caution light and oral. Caution messages will still be displayed on EICAS. Discrete amber lights will illuminate. At rotation, the warning oral and master warning light are also inhibited along with the caution inhibit. The rotation inhibit does not prevent warning messages from appearing on EICAS. The associated red discrete light will also illuminate. The inhibits end under two conditions. First, if the takeoff is aborted above 80 knots. The caution inhibit ends when the airplane slows below 75 knots. Also, at 400 feet or 20 seconds after rotation, all warning and caution messages inhibits end. Extinguish the master warning and caution light. When an engine is shut down, many of the individual alert messages on EICAS are replaced by an engine shutdown message. Shut down the right engine and observe EICAS. Notice that EICAS is not filled with distracting messages. The displayed messages describe the actual aircraft condition. Now shut down the left engine. When the airplane is on the ground and both fuel control switches are in cutoff, the master caution lights and beeper are inhibited for all caution alerts. Any new caution messages will only be displayed on EICAS. The master warning and oral, along with warning messages, are not inhibited under these circumstances. Let's look at the takeoff configuration warning. To illustrate this warning, select the thrust switch to advance the thrust levers for takeoff. As the thrust levers advance, the configuration warning alerts you if the flaps, spoilers, stabilizer, or parking brake are not set for takeoff. In this example, all four are not set properly. Reset the warning. The takeoff configuration warning consists of the warning light, the siren, and the configuration light. The EICAS message identifies the improperly configured item. The flaps message means the leading edge slats or trailing edge flaps are not in the takeoff position. Select Flaps 5 by touching the flap lever. The flaps are now at a takeoff setting and the flaps message is no longer displayed. No warning is given if an incorrect takeoff flap setting is selected. The spoilers message indicates that the speed brake lever is not in the down detent position. Set the speed brake lever in the down position. The spoilers are now in the down position for takeoff. The stabilizers message means that stabilizer trim is not in the takeoff range. Adjust the stabilizer trim into the takeoff range. Stabilizer trim is now within the green band. This indicates trim is within the takeoff range. The parking brake message indicates the parking brake is set with engine accelerating toward takeoff thrust. Release the parking brake. All takeoff configuration warnings have been corrected. Now let's look at landing configuration warnings. When the airplane is in the air and any landing gear is not down and locked, a configuration warning is given under two conditions. First, when the airplane is below 800 feet radio altitude and either thrust lever is at idle, or second, when landing flaps are selected. The landing gear is not down, thrust is at idle, and the airplane descends below 800 feet radio altitude. Silence the warning siren. Lower the landing gear to correct the configuration. The warning indication is canceled when the landing gear is down and locked. If required, you can inhibit the warning oral with the ground proximity gear override switch. Select it now. The oral is inhibited, but the lights and message advise of a gear not down. The second situation that causes a landing configuration warning is selecting landing flaps when the landing gear is not down. Select Flaps 30. There are two ways to silence the warning oral if the flaps are in the landing configuration with the landing gear up. You can either lower the landing gear or select the ground proximity gear override switch. For this example, lower the landing gear. Lowering the landing gear removes all warning indications. Let's go on to the next two warning situations. A stall warning system is available in flight to warn of an impending stall. Warning of an impending stall is given by vibrating both control columns. The last configuration warning is the overspeed warning, which occurs when VMO/MMO limits are exceeded. The overspeed warning lights, message, and siren remain activated until the speed is reduced. Retard the thrust levers. When the airspeed is below VMO/MMO, the overspeed warnings are no longer displayed. The status page is available on the lower EICAS display. Display the status page by selecting Status on the EICAS control panel. System indicators appear here, indicating hydraulic quantity in percent and hydraulic pressure. If servicing is required, a required fill prompt appears next to the quantity indication. APU, EGT, and RPM are displayed. Crew oxygen pressure is also displayed. Flight control positions for the rudder, ailerons, and elevators are displayed. Brake temperatures for each main wheel are shown in units from 0 to 9. Status messages indicate system faults. The messages are MEL related. Select Status to remove the status page. When the status page is not displayed and a new status message occurs, a status cue appears on the lower EICAS display. Check the new status message by selecting Status. The new status message displays. In flight, status messages do not need to be checked. EICAS alerts provide airplane status. Status messages are useful in anticipating possible ground maintenance actions. Let's take a closer look at the status messages. If there are more status messages than can be displayed on one page, a page 1 appears on the bottom of the list, indicating there is more than one page of status messages. The newest message appears at the top of the list. Select Status to display the next page. The oldest message appears at the bottom of the list. Select Status to blank the display after the last page. The Event Record feature is used to provide a system readout that may be useful to maintenance personnel. In this example, left hydraulic pressure is low and you decide to record the event for maintenance. Select Event Record. When Event Record is selected, a variety of system information is recorded into the EICAS computers. This data can be retrieved later by maintenance personnel. Each press of the Event Record erases any previously recorded data. Only the last event is recorded. Let's look at EICAS indication failures. We'll now focus our attention on the upper EICAS display. One example of an EICAS failure is a missing pointer and black digital display. In this example, the EICAS computer is receiving unreliable N1 sensor input from the left engine. With the EICAS computer selector switch in the automatic position, the left EICAS computer normally controls the EICAS displays. To check if the other computer can provide a reliable N1 indication, switch to the right computer. Select the right computer. The left N1 indication is restored. Now let's see how EICAS responds to a control panel failure. If the secondary indications are not displayed before the EICAS control panel fails, they automatically display on the lower CRT after the failure. The EICAS control panel advisory message indicates the display switches and the cancel recall will not function. The computer selector and the brightness control remain operative. Let's look at EICAS display failures. If the upper CRT fails, the complete display moves to the lower CRT. The air data computer and inertial reference system provides flight data such as position, speed, altitude, and attitude. For the flight displays, flight management computers, and engine controls. The major components of the air data system are the air data computers. The major components of the inertial reference system are the inertial reference units. First, let's look at the air data part of the system. The air data computers electronically supply pitot and static pressure information to the flight instruments and other airplanes. The air data computers are remote sensors which electronically supply pitot and static pressure information to the flight. The air data computers receive and process data from 4 pitot probes. 4 static ports, 2 per side, 2 AOA probes, and 1 TAT probe. The ADCs provide pitot and/or static pressure information to the flight instruments and airplane systems. The source of air data for flight instruments is controlled by the air data switch located on the forward instrument panel. Selecting alternate changes the source of air data to the opposite side ADC. Press the captain's air data switch to connect the left side flight instruments to the right ADC. The captain's instruments are now receiving data from the right side ADC. Now let's examine the IRU in more detail. Three IRUs provide navigation data for use by the flight instruments and FMS. Each IRU contains electronic sensors and non-mechanical laser gyroscopes, which measure airplane movement in all 3 axes. Signals from the sensors and gyros are used to calculate the airplane's attitude, heading, ground track, ground speed, and the airplane's latitude and longitude position. Before the IRU can calculate this information, it must accomplish a pre-flight alignment. Pre-flight alignment is the calculation of the airplane's relationship to true north and is done independently of any navigation aids. The IRU uses gravity to calculate the airplane's attitude and the Earth's rotation force to determine the location of true north. The airplane must remain stationary during pre-flight alignment to properly sense Earth gravity and rotation. The process usually takes 10 minutes. At high latitudes, alignment time is 17 minutes. To maintain navigational accuracy, a complete alignment must be accomplished when the time from the last full alignment exceeds 18 hours. Alignment begins with the IRS mode selector panel. The IRS mode selector panel is located on the overhead panel. An IRS must be aligned before it can enter the NAV mode. Rotating the IRS mode selectors from off to NAV begins the IRS alignment. AC electrical power is available. Position the IRS mode selectors for alignment. The IRS performs a short power test during which the on DC light illuminates. When alignment is in progress, the align lights illuminate. Alignment requires approximately 10 minutes. Present position, latitude, and longitude must be entered on the CDU to complete the alignment. You will learn in another lesson how to use the FMC CDU to enter your present position. The crew enters the most accurate present position available. If global positioning system coordinates are available, they are the most accurate. The IRS compares the entered position with the last known IRS position and the sensed geographical latitude. The FMC also compares the entered position against the coordinates of the active flight plan's origin airport. When the alignment process is complete, the IRS enters the navigation mode. And the IRS align mode lights are extinguished. Although the IRS is very accurate, after entering navigation mode, errors accumulate. To compensate for this, the FMC calculates its own position using both IRS position and other data. To provide navigational backup in case of dual FMC failure, the IRUs contain an identical magnetic variation table. Variation data for all locations between north 73 and south 60 degrees latitude is stored in both systems. The FMC is covered in detail in other lessons. When the airplane is secured, positioning the IRS mode selectors to off prevents discharging the main battery when AC Continue. Notice that the IRS display is blank. And after 30 seconds, the align lights extinguish. If an IRS mode selector is left in the NAV position and the associated on DC light illuminates, this indicates the IRS is using its backup power source of the hot battery bus. Undesirable drain of the airplane battery will occur. The ground crew call horn in the nose wheel well sounds, providing an alert that a battery drain condition exists. Let's look at IRS non-normals next. During alignment, the IRUs sense their position. They compare sensed position with the position you entered and with the position at the time the IRS was shut down. If a position entry is not made before the IRS completes initial alignment, the align lights flash and the CDU scratchpad displays Enter IRS Position. If no position is entered or if the position entered is more than 6 miles from the FMC active origin airport, the IRS Position Origin Disagree message is displayed. You must enter the position again. Entering the correct position allows the IRS to complete its alignment. The DC fail light shows that backup DC power for the IRS is not normal and would not be available if AC power is lost. However, if the other lights are extinguished, the IRS continues to operate normally on AC power. Normally, the IRSs operate on AC power from the left and right electrical systems. The main airplane battery is used as an alternate power source. The on DC light for the associated IRS illuminates, and the associated IRS on DC EICAS message is displayed when AC power is lost and DC power is being used. If the AC power loss is due to the complete loss of all generators, all three IRUs will use the battery for power. In this case, the right IRU will shut off after 5 minutes to conserve battery power. The IRS fault lights show that there is a fault in the selected mode. In this case, there is a failure in the right IRU nav mode. Because there is a failure in the right IRU, attitude and heading information are not available to the first officer's instruments. To make the attitude indicator available again, use the center IRS by selecting alternate on the first officer's IRS instrument source selector. For this lesson, turn the right mode selector to attitude. The IRU enters the align mode for 30 seconds, during which the airplane should stay in straight and level flight. This relevels the system and provides an attitude reference. When attitude alignment is complete, the align light extinguishes and the attitude information is available. In attitude mode, the IRS does not calculate acceleration, vertical speed, ground speed, track, position, heading, or wind. To display heading data, you can put in the current magnetic heading on the CDU position initialization page. Enter 127 into the set heading line. Regularly examine the IRS heading and, if necessary, put in a new heading. The Attitude Director Indicator, ADI, gives an electronic display of your attitude. A pitch limit indicator appears when flaps are extended. It shows the pitch attitude at which the stick shaker occurs. Each pilot has a switch for activating their flight director. Turn on the flight director by touching the switch. Command bars appear, and the flight director's operating modes are displayed. Touch the switch again to turn off the flight director. Correct. Selecting an ILS frequency tunes all three ILS receivers and displays the localizer and glide slope scales on both ADIs. Touch the selector to set an ILS frequency. The localizer and the glide slope scales are displayed. Pointers will appear when localizer and glide slope signals are received. The decision height selectors on the ADI control panels set the decision height for the radio altimeters. Set the decision height to 200 feet by touching the selector. The new decision height is displayed. Selecting a negative height blanks this display. Touch the selector to set the decision height to -10 feet. Now return the height to 200 by touching the selector. Correct. When descending through 2,500 feet, your radio altitude is displayed. If a localizer signal is being received, the green rising runway symbol is also displayed when the radio altitude is at or below 2,500 feet. When descending through 1,000 feet, an altitude height alert is displayed. The alert is turned off when the airplane descends below 500 feet AGL or climbs above 1,000 feet AGL. The alert can also be canceled manually by pushing the decision height reset switch. Touch the reset switch. The alert is removed. Below 1,000 feet, the digital radio altitude value is encircled by a round dial. The triangular pointer represents your selected decision height, 200 feet in this example. As altitude decreases, the circle around the dial disappears accordingly. Each tick mark around the dial represents a 100-foot interval. At 200 feet, the runway symbol begins rising toward the airplane.
Minimum.
When the decision height is reached, the display changes to amber and flashes. At 0, the display returns to its original colors. Notice that the radio altitude displays a negative number when the nose gear is lowered to the runway. With the approach mode selected, the ILS scales and pointers provide an alert if deviation becomes excessive. Below 500 feet radio altitude, with a significant deviation from the glide slope, the scale changes to amber and the pointer flashes. The localizer scale and pointer provide a similar alert if localizer deviation becomes significant. The display returns to normal when deviation is again within normal limits. Now let's discuss how the ADIs receive their information and what corrective action to take if failures occur. The left and right symbol generators normally supply symbol information to their respective ADIs. The center symbol generator is available as an alternate source. A failure of the selected symbol generator results in a blank ADI. Push the electronic flight instrument EFI switch to connect the center symbol generator to the ADI. Information is restored to the ADI and HSI through the center symbol generator. The 3 ILS receivers and radio altimeters supply information to their respective symbol generators. Localizer and glide slope flags indicate that the selected ILS receiver has failed. Push the EFI switch to connect the center symbol generator and ILS receiver to the ADI. Localizer and glide slope information are restored to the ADI from the center ILS receiver. This flag indicates that the selected radio altimeter has failed. Push the EFI switch to restore the display. Radio altitude information is restored through the center symbol generator and center radio altimeter. The left and right inertial reference systems normally supply the attitude display to their respective ADIs. The center IRS is available as an alternate source. You'll see pitch and/or roll alerts when the captain's and first officer's attitude displays are different, or an attitude flag displays when a complete loss of attitude information failure exists from the selected IRS. Push the IRS switch to connect the center IRS to the ADI. Attitude information is restored using the center IRS. This flag appears if decision height information is lost. No alternate source is available. The airspeed indication is a moving tape that displays current indicated airspeed at all times. 30 knots is the lowest indicated value. Current Mach is displayed at 0.40 Mach or higher. A speed trend vector shows predicted airspeed in 10 seconds based on the current acceleration or deceleration rate. Command speed and the command speed bug correspond to the FMS target speed when using VNAV or the current IAS Mach window setting. The mode control panel and IAS Mach controls are located on the glare shield. Command speed and the command speed bug correspond to the current MCP airspeed window setting. If the FMC is computing command airspeed, the window is blank. When the command speed is off scale, they are displayed in this location when the FMC MCP command airspeed bug, as selected by the FMC or IAS Mach selector, is above the displayed range. During pre-flight, the V1 INOP flag is displayed until takeoff reference speeds are entered through the CDU. The takeoff ref page shows calculated takeoff reference speeds. After the takeoff speeds are entered, the V1 INOP flag is removed. Because the V1 and VR speed indications are off scale, the digital V1 speed is parked at the top of the scale. V1 and VR will attach to the speed tape as they come into view. V2 is set as the command airspeed on the speed tape with this indicated airspeed IAS Mach selector. When the airplane is first powered, 200 knots is displayed. Rotating the selector changes the speed in the window along with the command airspeed on the ADI. Set the IAS Mach speed to 144 by touching the selector. The selected V2 command speed appears directly above the speed tape. During takeoff, the ADI speed tape shows acceleration. When V1, VR, and command speeds come into view, the V1, VR, and command airspeed indications change to bugs on the airspeed tape. The R bug represents the rotation speed entered in the CDU on pre-flight. As you continue to accelerate after takeoff, minimum speed and maneuvering speeds come into view. V1 and VR are still in view but are removed 2 minutes after takeoff. Minimum speed is shown here. This indicates the stick shaker speed. And F represents your normal maneuvering speed for the existing flap setting. It is not displayed above 20,000 feet. The top of this bar provides your minimum maneuvering speed. This is the speed at which a minimum of 40 degrees of bank results in stick shaker. As you continue to accelerate, Mach number appears when speed is greater than 0.4 Mach. Maximum speed is shown here. It indicates current maximum speed as limited by VMO/MMO, gear or flap placard speed. At higher altitudes, with high gross weight, a maximum maneuvering speed may be displayed. It indicates the maneuver margin to high-speed buffet. Prior to descent, a landing flaps setting and landing reference speed should be selected on the Approach Ref page. Select VREF for flaps 30 on the CDU. Now transfer the flap setting and associated speed to the flap speed line to display the speed on the speed tape. To start a deceleration, set the IAS Mach speed to 214 by touching the selector. As you reduce speed and begin your approach, the F bug shows the maneuvering speed for your current flap setting. As you select more flaps, the F bug moves down to the new maneuvering speed. VREF is positioned on the speed tape indicated by an R according to the entry in the CDU. Recall that R also represents VR during takeoff. Now let's discuss non-normal conditions as indicated by failure flags or messages. This message indicates that the command airspeed is inoperative. The command airspeed bug disappears. This means that the V1 display is inoperative and the V1 bug disappears. A speed limit message indicates that either the minimum or maximum speed display has failed. This flag means that the Mach display has failed. A speed flag indicates that the speed tape is inoperative. The entire speed tape display blanks. The HSIs are the lower of the two display units. The HSI presents a selectable color display of flight progress. HSI heading is supplied by the IRS. 3 primary display modes are available: Approach mode shows ILS approach information on an expanded compass rose. VOR mode uses a similar format for VOR data. Map mode presents FMC information against a moving map background and is the recommended mode for most phases of flight. Approach, VOR, and Map can also display in a center format. Center modes show a full compass rose. Plan mode displays non-moving map information and is always oriented to true north. Map and plan are covered in a separate lesson. These controls are used with the HSI. The mode selector is used to set the desired display mode. Since this lesson is not about plan mode, select VOR. Let's first look at the HSI heading track indications. VOR and Approach are both heading up displays. Current heading is shown in the window. Heading reference shows the orientation of the compass rose. This is covered in detail in the second HSI lesson. The top of the airplane symbol represents airplane present position. The track line indicates airplane track. The HSI uses the heading selector on the mode control panel. Set the heading to 250. Even though the heading bug is out of view, the heading reference line remains displayed to indicate bug location. Before we go through navigation radio tuning, let's look at the radio information that is displayed on the HSI. The source of the displayed navigation information is shown here. The left HSI displays left VOR data only, and the right HSI right VOR data. The left HSI normally displays left ILS information. But should that source fail, the center ILS data can be selected. The right HSI follows the same logic. The course pointer positions to the selected course. DME, if available, is shown here. Course deviation is displayed on this scale. The glide slope scale displays only in approach. In VOR and approach mode, the course deviation indication remains unfilled at all times. The to from indication only appears in VOR mode. ADF pointers and information are green. Left ADF pointer is a single line. Right ADF pointer is a wider double line. Next, let's look at the NAV radio page. The NAV radio page allows the VORs to be tuned. VOR frequency, tuning status, and identifier are displayed. The tuning status A indicates automatic tuning, which is the normal FMC operating mode. R displays if a VOR is tuned by the flight crew on the NAV radio page. P indicates the nav aid is a required part of the selected approach or departure procedure. Manual tuning is shown by an M. Manual entries tuned by the VOR DME control panel are accepted at any time, regardless of the current tuning status. For remote tuning, valid entries are frequency or VOR identifier. Now, let's see what happens when you enter a frequency of 110.90 for the left VOR. Enter this data into the correct line. The invalid entry message occurred because 110.9 is not a valid VOR frequency. Frequencies from 108.10 to 111.95 with odd tenths digits are not allowed. Clear the scratchpad message. Enter the frequency of 115.70 for the right VOR. A VOR can be returned to auto-tuning by deleting the current frequency. Use the Delete key to delete the right VOR frequency. Continue. Additional tuning data can be stored for later use on the pre-select line. Any valid format for any line on the page is accepted. Use the pre-select data to retune the right VOR receiver to the SLI VOR. Now let's look at a few miscellaneous HSI indications. Wind data is displayed as a readout, and a wind arrow oriented to the compass rose. Weather radar and TCAS data can also be displayed. The traffic switch toggles TCAS traffic symbols on and off the HSI. Push the traffic switch to remove the TCAS data. The weather radar map switch toggles radar information on and off. Both TCAS and weather radar are discussed in other lessons. Notice the range information. The number equals 1/2 the actual range setting. The range selector controls the displayed range. Set range to 160 miles for a quick weather check. Before discussing non-normals, let's look at how center displays are different from expanded displays. The center switch toggles the HSI between expanded and center modes. Approach, VOR, and map can all be displayed in the center mode. The center switch is inoperative when plan is selected. Now push the center switch. The center format remains in effect when changing. Now let's compare the center and expanded approach modes. The most obvious difference between expanded and center modes is the compass rose. Notice the airplane symbol has changed. Present position is now at the center of the symbol. The selected heading line is not shown on a center display. but the selected heading bug is always in view. The selected course pointer is a different shape, and the glide slope scale is positioned higher on the display. Course deviation indications and deviation alerting are identical in both modes. In VOR, the to from word is accompanied by a conventional triangle symbol in center mode. Finally, center VOR and approach do not indicate range. In this lesson, we'll look at the horizontal situation indicator display map and plan modes. Map mode presents FMC information against a moving map background. FMC present position is shown at the top of the airplane symbol. Map can also be shown in a center format. While center map shows the same total range as expanded map, the forward range is only half the expanded distance. Plan mode displays non-moving map information in a center format, but always oriented to true north. We'll discuss plan later, but first, let's look at some differences between the map and VOR approach displays. Map is a track-up display. The track line remains vertical at all times, and the current heading pointer shows airplane heading. The selected heading marker and reference line indicate the heading set in the MCP heading window. Set the selected heading bug to 170. The selected heading marker moves to the heading set in the MCP window and remains displayed at all times. Now let's look at some common symbology like active waypoint information, full-time range display, a position trend vector, an altitude range arc during climbs and descents, and VNAV path deviation. The VNAV path deviation scale and pointer indicate up to 400 feet deviation. A readout appears when deviation indicates more than 400 feet. The indication is in view during VNAV descents, as long as a valid descent path exists. The display is removed after passing the end of descent point, or when either glide slope or flare mode engages. The altitude range arc shows where the MCP selected altitude will be reached. It is always displayed centered across the track line. Altitude range arc position is calculated by the FMC using current ground speed and vertical speed. These map switches allow additional items to be shown besides the basic FMC route information. Touch the various map switches for an example of their displays. Now select Plan on the EFIS control panel. In Plan, the top of the HSI appears the same as the map. The lower part of the display is a static map of your route oriented to true north. The waypoint at the center of the display matches the location of center on the route legs page. The step prompt allows you to step through and center each of the route waypoints. The RDMIs and heading reference switch are located on the center instrument panel. Heading reference indicates the current compass orientation as determined by the heading reference switch. The normal pre-flight position of the heading reference switch is normal. In normal, switching between magnetic and true heading occurs automatically above 73 degrees north latitude and below 60 degrees south latitude. While operating in the vicinity of a pole, notice the heading flag displays has deployed on the RDMI, but the HSI reference is true. Select True on the heading reference switch. Notice that the display on the HSI did not change, since the system was already in True. The RDMI heading flag is removed and True heading is indicated. The white attention box remains in view as long as True heading is selected. Anytime the RDMI and HSI are referenced to true north and the airplane descends 2,000 feet, at more than 800 feet per minute, the attention box turns amber and flashes for 10 seconds. The box returns to white when the airplane climbs 2,000 feet at more than 500 feet per minute. Position the heading reference switch to normal. When the reference returns to magnetic, a green attention box displays for 10 seconds. HSI failure flags replace the appropriate display to indicate source system failure or lack of computed information. The standby flight instruments are located on the center instrument panel. They include an attitude director indicator, a standby airspeed indicator, and a standby altimeter. A standby magnetic compass is located on the center post above the glare shield. These instruments provide a standby source of critical information in the event of primary display system failure. The attitude director indicator is powered by the standby electrical system. Pulling the caging control aligns the horizon line with the airplane symbol. The ILS selector allows you to display localizer and glide slope information on the attitude director indicator. Localizer and glide slope deviation are displayed. When ILS is selected, the localizer pointer provides correct sensing for front course approaches. A gyro flag means the attitude indication is unreliable. A localizer or glide slope flag indicates the center ILS receiver has failed. The standby airspeed indicator and altimeter inputs are pneumatic. Their static pressure source is the alternate static system. These instruments require no electrical power. These air data instruments receive information from the left and right auxiliary pitot probes and the alternate static system. The standby airspeed indicator displays airspeed in knots. The standby altimeter inputs are pneumatic. This instrument requires no electrical power. The alternate static system provides altitude information to the standby altimeter. The standby altimeter also has a pointer and a digital display. The selected barometric reference is displayed in millibars and in inches of mercury. Turning the standby barometric selector sets the desired reference for barometric correction. The standby magnetic compass is the liquid type and is internally lighted. A deviation card is located below the compass. The clocks are located on the left and right instrument panels, just below each VSI. Let's use a larger clock as we discuss the clock controls. The date switch is used to display and set the date and time. The clocks are located on the left and right instrument panels, just below each VSI. To switch between universal time, GMT, and the date, push the date switch in the upper right corner. These clocks only display GMT. Let's use a larger clock as we discuss the clock controls. The GMT date selector is used to display and set the date and universal time. Let's set the universal time. Use the clock set selector to manually set the clock to 9:10. First, move the clock set selector to the hours HSD position. HSD means hours, slew, or day. The hours begin to cycle. When the hours reach 9, the clock set selector is immediately moved to the minutes MSM position, where the minutes start to cycle. MSM means minutes, slew, or month. When the minutes reach 10, the clock set selector is immediately moved to the hold position. In the hold position, the clock is stopped. HLDY means hold or year. Begin running the new universal time by selecting Run. The clock now runs the new universal time. Push the GMT date selector to display the date. The day and month are alternately displayed with the year. The date displayed is June 7, 2008. When the date is displayed in the time date GMT window, the clock set selector is used to change the date by selecting the day, the month, and the year. Changing the date is accomplished the same way as changing the time. For now, push the GMT date selector to display the time again. Correct. The elapsed time selector controls the elapsed time function. and the chronograph switch controls the chronograph. The lower window displays elapsed time and chronograph time. In this example, the elapsed time function has been running for 17 hours and 12 minutes. Reset the elapsed time by selecting Reset on the elapsed time selector. The elapsed time selector is spring-loaded to return to the hold position. To begin timing, select Run. The elapsed time window displays only hours and minutes. After 1 minute of elapsed time, 1 displays. When you need more accurate timing, such as during non-precision approaches, use the chronograph function. Start the chronograph by pushing the chronograph switch. The chronograph uses a pointer hand to show seconds. Notice that the chronograph does not display seconds. Hours and minutes are displayed here and override any previously started elapsed time. When the chronograph is displayed, the elapsed timer runs in the background and is displayed again when the chronograph is reset. Push the chronograph switch again to stop the chronograph. Now push the chronograph switch again to reset the chronograph back to 0. Subsequent pushes start, stop, and reset the chronograph again. Notice that the elapsed timer, which was running in the background, is now displayed. A separate clock switch is located on each end of the glare shield. The clock switch acts as a remote chronograph switch for each of the clocks. This completes the instruction section of the lesson.